All right, so 0.68, when put in, actually there's also the percentage, atomic packing factor in percentage, meaning it to be 68%. So meaning 32%, so 100 minus 68. It means 32% of this cell is void, okay? Then with a simple one where we had 52, 0.52, meaning 52%. So 100 minus 52% gives us what? 48, huh? So it means 48% of the simple cubic structure is void. That's basically the interpretation that we can use to better understand the atomic packing factor in this case. All right, so we move to the next one. The face-centered cubic structure, FCC. So like I said earlier, with the FCC, we have atoms on this face of your cubes. Okay, the face-centered cubic system. The atoms touch each other along the face diagonals. So if in the case of the body-centered, it was only when we run a diagonal from this end to this end inside, you know, inside our cube, only then were we able to achieve a diagonal that has atoms throughout and no void. In the case of face-centered, you don't even need to try and run inside because there'll be a void. For this one, it's in the this outer face. You can see this outer face, isn't it? So meaning when I run a diagonal from here down here, there's no part of this diagonal that is void. So this is the one. This is the side that we're going to work with, or the face that we're going to work with for our diagonal in order for us to calculate the APF. So again, all atoms are identical. The face-centered atoms are shaded differently only for ease of viewing. As you can see here, this nice structure here. This is trying to depict what's here, okay? So these red ones are the ones in the corners, okay? The atoms in the corners. Then these are the atoms that are on the faces. On this face, for example, you have this atom. This face here, you have this atom. This face on top, that atom. At the bottom, you have an atom there hiding. And on this side also there's an atom there hidden. You just see part of it here. Basically coming to this shape or this one for better illustration. So you have this face, there's an atom. This face has an atom. This one here, this atom. As well as the top one, that's atom there. Now how do we get the coordination number? How many atoms are in this cell? Can you calculate together? Anyone willing to give it a try? No one is willing to give it a try. Okay, let's do it together. So the easiest are these ones in the corners, isn't it? There are 8. 8 corners, and they are 1/8, isn't it? So we have 8 corners times 1/8, which gives us 1 atom, isn't it? So all these added together, the 8, give us the 8 corners, give us one, make up 1 atom. Then we have the spaces. The faces are half an atom, okay? So there's a half the atom inside this cube, and the other half is in the next cube. So we can't see it. So we're just interested in 1 cube, so we just get the half. So we have the half from the face here, half from this face, half from this face, that face, and so forth. How many faces are there again in a cube? How many faces does a cube have?
6.
It has 6 faces. So on each face, we have half an atom. So 6 times half gives us what?
3.
It gives us 3. So what does this mean? It means that the halves that are collected from the 6 faces, when you put them together, you make actually 3 whole atoms. So meaning 3 plus the 1 atom, the 8 times 1/8 gives us what? Total.
4.
It gives us 4 atoms in the unit cell. Are we together? Examples that we have of the of metals that have this arrangement, this type of arrangement of their atoms is aluminum, copper, silver, lead, nickel. These are some of the examples. Gold, platinum, they have such kind of an arrangement. Okay, so again, closely here. So we say that for calculation, we pick this face, huh? Or this face, because this is the one that has the touching here. So we're using this formula, the cube root of A on this side. So for the length, the close back directions, you have your 4R. Again, I hope you understand why it's also 4R. We have half here, isn't it? So you have R plus R plus R plus R. So 1R, 2R, 3R, and 4R, giving us 4R for this diagonal, which is equal to, according to geometry, it's the square root of 2 multiplied by A. So meaning A is equal to, when you put your A here, when you solve for A, it's 2 times square root of R times R. Are we together? This formula when you solve for A. And we
Yes.
just a reminder, we say that each unit cell contains 4 atoms. So you have your 4 here, 4 over 3 times 5. And then here, when you put your R, when you solve it, when you solve for R here, what are you getting? Square root of 2 times A divided by 4, isn't it? That's what you have here to the power 3 over A3 here. Are we clear up to this point? Just like we've been doing in the previous ones.
Yes.
We do together. Okay, then from there, when you solve for the APF, you find that your answer is 0.74. 0.74 is our answer there. So again, this would be 4 times 4, 16, huh? 16 over 3, 5. R squared, isn't it? If you want to use R, you can use R. So if it's R squared here, so if you use R squared here, isn't it? It means you have to use this formula, A with R. You place it down here. When you place it down here, you find that your A's will cancel. Okay, they'll cancel out. And in the end, you just have the numbers that you calculate and find your answer. And your answer is going to be 0.74. Are we together? You can use that method also. So you just simply get this as your A, isn't it? Place it down here. And then this whole thing, you just write R here so that your R is cancelled. Or you can maintain the A and have the A's cancelled to find the final answer, which is 0.74. So this is the maximum achievable APF, 0.74. So meaning this one is run much more closely packed. So this one is more packed, FCC is more packed than BCC. Do we all agree? BCC was 0.68 and the FCC is 0.74 atomic pattern factor. So meaning in here, they are a bit more closely packed compared to the body-centered cubic structure. Then we come to, this one is really a bit more complicated, but I hope we'll grasp it at least just the general overview. So in the hexagonal close packed structure, the HCP, Examples of HCP, we have manganese, cadmium, titanium, and zinc. Chewe, are we together? Is it clear so far? Somehow.
I'm following.
You're following? No, that's a good answer.
Yes.
Okay, anyone with questions here? Because if we have lost you behind the side here, I think we should just be safe. Anyone who wants us to go back, please don't feel shy.
I think if we can go back a bit.
Okay, to which one? Or to everything? Where do you want me to go back?
Yeah, right from this page.
Okay. Are you clear with a simple structure? This one you've understood?
Yes, that one is understood.
This one is clear. Okay.
Yeah.
So here, so what exactly? Are you this part, this slide, or the next slide? This slide? Where do I start from? Should I start
The
from
previous
here?
slide.
Pardon, the second one, this one?
Yeah, the other one.
This one.
Yes, this one. Yes.
Okay. So body-centered cubic structure. With a body-centered cubic structure, there is a middle, there's a middle atom, or there's an atom that is placed right in the center of your unit cell. Okay. So aside from the ones in the corners here, you also have a host atom that is squeezed right in the middle there. Okay, and so meaning when this one is squeezed, when this atom is introduced in the middle, it simply means that right now, it simply means that now these ones are not touching, okay? Because there's one that has been introduced in the middle. It means now your corner ones are not touching there in the center. They're now leaving space to accommodate the one in the center here. So the one in the center is now the one that is touching all 8 of these, okay? All 8 of the corner atoms. These are referred to as corner atoms. So the one in the middle is touching all the 8 corner atoms. In this case, this is just to help us understand where it's located. Otherwise, this is how it's supposed to be. This is how it looks like, including this 3D arrangement here. So you have your 4, as you can see. So just imagine you get one football, isn't it? And then just stick 8 balls in this 8 on top. I mean 4 on top and 4 at the bottom of your football in the middle. That is how this arrangement looks like. So what does that mean also? So when you get one football and then you stick 4 in the top side, isn't it? That attach the 4 attaching and attaching the middle one, the center ball, this one here, and the 4 attaching there at the bottom. So it means that the diagonal that you can run here without touching any void is the one that is coming from there through the center atom up to this point here. That is the only diagonal that you're able to achieve that will not go through a void. If you try to do this one, there'll be a void here because these are not touching. These ones here are not touching. So you can't run a diagonal here, there's a void here. there's an empty space. It won't work, our formula won't apply. You can't run here because it's running through empty spaces. So the only diagonal is from this point inside up to this point. So that's the diagonal we'll work with. In terms of the coordination number, that is the number of atoms in the unit cell. We calculate as follows. Number of atoms inside this cube, you have one whole atom, isn't it? Inside here, it's not shared by any other unit cell. It's only found inside this particular unit cell. So we say one, this is the one center atom here, plus these corner ones. So these corner ones are 8. Okay, they are 8 and they're shared by 8 lattices. So meaning 8 times 1/8, that's the size. So each lattice here has 1/8 of the atom. So you have 8 times 1/8, which gives us 1 here. So you have 1 plus 1. So in short, you have the one body plus these 4. When you put these small pieces together, they make up 1 atom. Is it clear? The person that asked.
Yes, it
It's
is.
clear now.
It's making sense.
Making sense, eh? Okay. My maths teacher my math lecturer always used to say, if it's not clear, it will make sense in the exam. But I don't agree with him. No, I said, it's not clear, don't worry, it will be clear in the exam. He always used to say that, but I want it to be clear with you now. Okay, so we move now to the calculations. Huh? So here, this is an illustration to help us understand the diagonal that we're working with, the diagonal that we picked, this one. So this diagonal that we picked is touching this atom, radius, the middle one, the whole lot of it, and this other radius here. So you have this one, this atom being represented by this one here, this radius here. And then this, the one in the center, the whole atom is this one here, the whole atom. And then this one by the corner here is represented by this one. So you have this half here coming here, the radius here, that is 1 ara, the ara, the first ara, then the second ara is up to the center of this atom. The third ara is up to here. And finally, the last ara is this one here, which gives us 4R. So 1, 2, 3, 4. 4 R's are equal to this diagonal. And this is from geometry, okay? This formula is gotten from geometry, which will give us the square root of 3 multiplied by A. A is this distance here. So this is the Pythagoras theorem. This is the triangle we're working with, like that, and like that, where we have the brown line. So it's this triangle. This is the one that we're trying to do Pythagoras theorem, if you still remember Pythagoras theorem. Okay, so move forward. The formula here we're given already. Yeah? This is the APF is equal to atoms in the unit cell times the volume of the atom divided by the volume of the unit cell. So the number of atoms in this case, we're using the number 2, isn't it? Because of this one plus the coordination number, that is basically the atoms per unit cell. So we have 2 atoms here, multiplied by the volume of each atom, isn't it? The volume of each atom, this is the formula, divided by the volume of the unit cell. So we say the volume of the unit cell is, the volume of the unit cell, we use the formula for the volume of the cube, which is H cubed. In this case, we're saying A cubed because we're using A to depict the size. So A cubed, that is the volume of the unit cell here at the bottom. Then the volume of the sphere is what we're using here, 4/3 pi r cubed. So r, we replaced r with this, isn't it? With A. Using this, the 4r is equal to 4r, the 4 radius is equal to According to Pythagoras theorem, it's square root of 3 multiplied by a. That's the length of this side. So when you solve for r, you have square root of 3 times a, you divide it by 4, isn't it? Divide this side by 4, it will give you r. Divide this side by 4, it will give you square root of 3 times a over 4, which is what has been given here. So the power 3 according to the formula. Multiplied by a to the power 3. You have it here. So I said there are two ways to solve for this. You can solve using r or using a. If you want to solve using r, it means that you are going to leave your r here as it is, to be r cubed, isn't it? According to the formula for this here, to be r cubed. Except here, instead of putting a cubed, meaning you're going to get a from here and place it here. Then that's where you cancel out the errors to find your answer. Or you can simply get it as it is there and try and remove your mathematically. I'm not just saying just remove like that. Mathematically, I'm sure you know how to do that. You remove your a mathematically from there and you find your answer there, which will give you 0.68. Anything I've left out? Is it a bit clearer now for everyone? Well, now everyone is just lost now, confused. It's okay, it's normal to be confused at this point. I just grasping as we go, as we solve examples. I think that's one thing I didn't do. I think I'll come up with examples in our next lecture so that we look at each and every example together. So in some questions, some exam questions will be given a, the value of a, okay? When you're given the value of a, this distance, it's easy for you to solve, isn't it? Sometimes you'll be given the value of r, the radius will be given to you. So when you know when you're given r, meaning you simply place your r's there, it will be easy for you to find the answer. Sometimes you won't be given, just it as it is, and you just have to cancel out. But most likely in exam questions, you'll be given the value for a, which is that length, or you'll be given the atomic radius. And the atomic radii for most elements, most metals is already known. There's actually a table that we looked at earlier on, which was giving us the A values. So a question will come, calculate the atomic packing factor for copper, what. So already you know, and they'll give you say calculate the atomic radius if the APF is such and such. So sometimes in the exam you'll be given this value, okay, and you'll be asked to calculate the atomic, sorry, not the A, but usually you'll be given to calculate for the atomic radius. So you'll be given this value, and if the examiner is kind enough, I may give you the formula itself. But when I give you kindly mute your mics. When I give you the formula, obviously, usually when you're given a formula in the exam, there's no free lunch in the exam. When you're given the formula, most likely it means that there are some units that need to be converted. Okay, that's a trick I'll give you right there and then. Usually when the examiner provides you with a formula and even provides you with everything, including the formula, you should always get suspicious, because it means that most likely the units are not in order. And that's where the homework is, for you to now start calculating the correct, converting to the correct units, for you to find the correct answer. Don't always rush to calculating. Always make sure that the units are correct. So face-centered cubic structure. In this one, we have the usual 8 in the corners there, plus an additional 6 half atoms. So there's an atom here, that's half of it is inside this unit cell, half of this one inside the unit cell. At the top there, there's another half, at the bottom a half, this side. So in short, every side, which is 6 sides. So 6 sides have half an atom each. So 6 times half gives you 3. 3 plus the 8, the usual, times half 1/8 here, which is 1. And this one already know the answer by now. So meaning 3 plus 1 gives us 4 atoms. So when you put all these together, they give us 4 atoms in this unit cell. That's the arrangement. Examples of such are aluminum, copper, are the ones that have this kind of packing, atomic packing. And this is how we solve for it. So for this one, we solve using the phase. Okay, any phase, pick any phase. And you run a diagonal. You find that where you're running the diagonal, there's no void. The diagonal is perfectly running along or through atoms, along the atoms. So let's use the word along. So according to Pythagoras, again, this side is square root of 2 multiplied by a. That's the length of this side. So, but according to us, our packing factor, I mean, the way our atoms are packed here, according to this direction and how our atoms are packed, there's a half an atom here, a full atom here, which is 2r, isn't it? Plus another half. So you have half, plus another r. So you have an r here, another r here, and 2 r's here. So 1, 2, 3, 4 r's. 4 r's is equal to this formula. So when you put a here on the side, this is what you get. So you can simply get this in place of a. So you have 2 times square root of 2 times r in brackets to the power 3. Okay, that is what you place here in your a. You can do that. Same as here, you can remove everything and simply put your r. Then this r at the bottom there and the r here at the top, mathematically you cancel them out, and the answer that you get is 0.74. 0.74. Any questions? So examples there are copper, aluminum, nickel, silver have this type of packing. So 0.74 means that when you put it in percentage form, this is 74%. 0.74 times 100 is 74%. So means 74% of this unit cell is occupied by atoms. The space is taken up by atoms. So meaning which space is not taken up by atoms? 100 minus 74%. That is the void space. So what's 100 minus 74? 26% of this, isn't it? 26% of this is actually just empty spaces. That's what it means. That's the interpretation of the atomic packing fact. I hope we're together now. We move forward. So we have what is known as this is a slightly complicated one. The hexagonal close packed structure, HCP. Okay, it has a sequence. There's the AB stacking sequence. And there's their sites. There's the A site, the B site, these are the A sites, and these are the B sites. The middle layers are known as the B sites. Your distance, your A distance is here. Then there's an introduction of a new distance, which is the height, or in this case, it's just simply known as C. So you have your hexagon, isn't it? There is a hexagon. They are like that. How many sides does the hexagon have? In 2D. It's 6 sides. Huh? So you have 1, 2, 3, 4, 5, and 6. So each corner has an atom, as you can see. These are the 6 sides. So there's this side, this side, this side, this side, and this side, and this one. So 6 sides. Then your middle layer there has how many atoms? 3 atoms. So you have 6 atoms there, and the bottom also has 6 atoms, isn't it? And then you have your middle layer there inside. inside the layer which has 3 atoms. So for this one, how do you think we calculate? How anyone with an idea, how anyone to help us, or let's try and do it together. Let's calculate the coordination number. That is the number of atoms found in this one. Let's start from the top. Or maybe someone to help us. We've seen the number is 12 here. Anyone help us understand how it comes to 12? Anyone to try?
I'm counting 7 on top.
You're counting 7. Oh yeah, plus the one in the middle, isn't it? Yes, so
Yes.
sorry, yeah, 6 plus 7, thank you. Yeah, so 6 and the 7th one here in the center. So now you have to remember that. Remember what we said, there's another hexagon here coming up. Okay, so there's sharing happening of these atoms. They don't wholly belong to this particular hexagon. Are we together? So the way there's this hexagon, isn't it? There's another one stacked, exactly looking like this one, stacked here on top. So they are sharing these atoms. So these atoms are being shared by other units, other cell units. Just like we looked in the previous examples. Remember we had like 1/8 for these corner ones. Maybe just using our imagination, how many atoms do we think? Okay, let's begin with the center ones. Maybe they'll be the easiest. Which portion of the center atom do you think is belonging to, or is found in this particular cell unit? Half, isn't it? If there's another one here on top. So meaning half of it is down here, then the other half is belonging to another cell unit that's stacked here right on top. I hope we're all getting it. Then look at these 3. Look at how they're located. Look at them from the top. Do you think they're shared with any other cell unit? Look at them from here and look at how they are arranged from the top. And look at the cell unit from the top. Do you think they are shared by any other cell unit? The middle layer?
No.
No,
those
right?
Seems to be closed.
Okay, seems to be closed. So we have 3 whole ones to this belonging wholly to this cell unit. You have the 3 here, and then you have a half here, isn't it? Alternatively, you have another half here because there's another cell unit here continuing, and even in the sides here, the other cell units stuck. So you have this half here and this half here, isn't it? So you have 3 here, and this one forming 4, isn't it? So you have 3 here and the half here for the center, plus this other half to form a one whole atom, isn't it? I hope we're together. I hope I've not lost anyone.
Yeah, together.
We're together. Eh? What do we think about the corner ones now? How do you think they're shared?
Half.
Hmm? They're shared by half.
No.
Let this be our homework. Let's look at this, okay?
Okay.
Then look at this. Please don't forget. Have a look at the hexagons and how they are shared, how we derive the coordination number equal to 12 and the APF as 0.74. You can use the Calista textbook. If you've not yet downloaded it, please download it. Very helpful. So next lecture, I'm going to hear from you how to calculate for the number of atoms in the hexagon, in the hexagonal cross-path structure. Okay. So we move forward. So we find that FCC and HCP are highest density packing. Remember, it also has an APF of 0.74, just like the FCC. So FCC and HCP are highest density packing schemes. So this illustration shows their differences as the closest packed planes are built up. So it's just basically illustrating to us how the stacking is happening along the planes. So this is a hexagon. You have the packing here, the packing here, the packing on top, and here at the bottom. So there's one atom here, and then the other two here, making it 3 in the middle layer. Then the top layer has the 6 here plus the body centered one here, which is the 7, and same as the one here. Then for the face-centered cubic, there's a cube here. It's a bit confusing, but if you follow the planes, you find that along the planes here, you have the body the face, the one on the face is here, isn't it? The corner ones, the 4 atoms plus the one on the face. Then you have here the one on this face and the one on this face. The one on the face here and the face behind this A, this face is this one. So they form a plane, basically. Same as the one here on this face, the atom, and on this face, and on the other face behind, they also easily form this plane. So if you draw the diagonals, and then you join the atom centers there, you also find that they also form another plane. Then we come to what is known as the theoretical density. So it's also possible to calculate the theoretical density of atoms using this particular formula. So using this particular formula, the density is basically the mass of an atom in unit cell divided by the total volume of the unit cell. So you have your Na, N is the number of atoms in unit cell. So for BCC, the number of atoms was how many? Do we remember? In the unit cell, what was the coordination number? We had for body centered, we had the whole atom in the body, isn't it? 1 plus the corners making up 1 atom. So we had 2. So if you are calculating for BCC, meaning here you have 2. Number of atoms per unit cell will be 2 here. Atomic weight, for example, if you have copper, what is the atomic weight of copper? It would be 65, isn't it? 65.5, somewhere there. Then the volume of the unit cell, when you may be given or you may have to calculate. So for a cubic, it's a cubic, what we've been looking at is A cubed. That is the volume of a cube, A cubed. And then Avogadro's number, Na is Avogadro's number, which we know, isn't it? 6 times 0.23 times 10 to the power 23 atoms per mole. So everything here is basically known. You already know how to calculate. Then you find your density there. So just understanding there, an example is for chromium. Find the theoretical density for chromium. Chromium, you've been given a hint, it's BCC. So you've been given your A, 52 grams per mole, atomic weight of chromium. The radius of the atom is 0.125 nanometers. Then the N, we know that the number of atoms per unit cell for a BCC structure is 2. So therefore your A, you calculate your A, isn't it? You've been given R. So like I said in the exam, you may be given R, your radius. So you simply put it in this formula and you get your radius there. I mean your length, sorry, your A length, which you can easily calculate for. So you have your atoms per unit cell 2 times 52 grams per mole there, volume per unit cell